Okay, so welcome back. In this video, we're going to pick up on BJT transistors, or BJTs you could just call them, and we are going to consider the NPN BJT. So in the last video, we talked about our three modes, our active, cutoff, and saturation modes, and all of the semiconductor physics of the N-type and P-type. I'm going to put that aside for now. But we really have to ask, what does it mean to be in the active mode, or what does it mean to be in the saturation mode or saturated? The cutoff mode is pretty straightforward. You cut off all the current. Now let's recall the formalism that we developed in the Intro to EE course. So we have, again, some base current IB, some collector current IC, and some emitter current IE. And what we understood was that for some small base current going base to emitter, it allows for a large collector current, which kind of gets grouped into the emitter current. Now what we can say is that the emitter current is equal to the base current plus the collector current. And we're going to relate the base current and collector current by this value called beta, such that we can say that the collector current is equal to beta times the base current, and we define beta as the gain. Now from this equation up here, we can substitute what we just defined, and we can say that the emitter current is equal to the base current plus beta times the base current. That's going to be our collector current. Simplify that a little bit, call it 1 plus beta times the base current, or we could say in terms of the collector current that it's 1 divided by beta plus 1 multiplied by the collector current. Now we can define something called alpha, which is the collector current divided by the emitter current, and that's just going to be equal to beta divided by beta plus 1. Now if beta is quite large relative to 1, we can say that alpha is approximately 1. Now in practice, you might expect beta to be in the range of 10, even all the way up to 1,000. Now if we start to talk about saturation, well, saturation doesn't allow for the collector current to keep following this beta times IB value. This relation is what works in the active mode. And then we can just restate that the cutoff mode means that the emitter current is equal to 0. So let's look at an example. So we're going to have an NPN transistor here, and you can easily tell by the arrow inside. I'm going to say that our gain is equal to 100, and we have some circuitry hooked up. We have a 10K for the resistor to the base, a 5K for the resistor to the collector. We have a 10 volt source to the base and a 15 volt source to the collector. Our emitter is simply tied to ground. Now, if we make a KVL from this 10 volt source going through the base to emitter loop, what we can say is that the 10 volt source minus the voltage over that 10K, which is just going to be the base current times the 10K, minus VBE, that's going to be equal to 0. And what is VBE? Well, it's the voltage developed between the base and emitter, and ironically enough, even though we said that NPNs or BJTs cannot be modeled by simply a set of diodes, well, VBE is approximately 0.6 to 0.7 volts. The life of irony. Now, if we make this assumption, we can say that the base current is going to be 10 minus 0.6 divided by the 10K. So our base current is going to be 0.94 milliamps. Now I might switch it up if I use 0.6 or 0.7 volts, just to give some variation in the problems. Now we can find our collector current, which is going to be equal to beta times IB. We know what IB is, we know what beta is, so we can find our collector current. That's going to be equal to 94 milliamps. But now we want to check something. Let's see what VC is, and this might tell us something about what mode we're in. So if we do a KVL for the collector side now, we can say that this voltage for the collector minus the voltage drop over that 5K resistor, well, that's going to be equal to what VC is, which is also going to be equal to what VCE is, because the emitter is just tied to ground here. So if we plug that in with our value for IC, which was 94 milliamps, well, we get that VC or VCE is minus 455 volts. Which seems a little bit odd from the rules that we defined for how the modes operate, and this is when we realize that we are now saturated. Another example here, we can see that we have a 4 volt source directly tied to the base of the NPN, no resistor there, but now we have a resistor on the emitter to ground. We have a resistor between our 10 volt voltage source and our collector, and we're going to assume that VBE is 0.6 volts in this case. Now, again, we can set up a KVL for this loop here from the base to the emitter. So we know that we're going to have 4 volts. We know that we're going to have a voltage drop from the base to the emitter. So this point at the emitter would be, 3.4 volts. So we'd have 3.4 volts divided by this 3.4K resistor. So we could actually say that the emitter current is equal to 1 milliamp. Now again, we're going to say that beta is equal to 100. So we could actually say that the collector current is equal to 1 divided by beta plus 1, which we derived above. And then we want to check, so we can say, is VB greater than 0? Is VC greater than 0? Is VCB greater than 0? Well, perhaps, maybe it is. You can check for yourself to verify that. And then from that, we really ask ourselves, does this satisfy the active mode? Is VC greater than VB greater than VE? It appears so. So now we are in the active mode. So we went through two examples, one that showed us that we were in the saturation mode, and one that showed us that we were in the active mode. But we still have no idea how to analyze the first example if we're in the saturation mode. We can just say that we are in the saturation mode because logically it doesn't make sense. If we're in the active mode, the math doesn't work. So in the next video, we'll actually hop into what saturating a transistor or BJT really means. Thank you for watching. If you learned anything new, please like, comment, share, subscribe. Helps out the YouTube algorithm.